All right, so this is Markov Chains video 1. So what I want to do here is start with an example and work through some calculations and come up with a general statement, but not do any really deep analysis. So consider, for example, the following situation. Imagine a population is distributed into one of two states. So a population is distributed into one of two states. We'll say state 1 and state 2 for now, but it could be anything. You can think of them as physical states or states of being or anything like that. Okay? So we'll say to start, 0.7, think 70% is in state 1 and 30%, 0.3, is in state 2. So suppose they sit in their respective states until some time period ends. So at the end of some time period, doesn't really matter, like a day, an hour, they might move, right? They might change states. So suppose the following happens. Suppose from state 1, what we'll say is, we'll say 90% of them stay. So 0.9 remain in S1 and 0.1, 10% go to S2. And then from S2, notice there's up to 1, of course, because everybody does something. So from state 2, we'll say, say 0.05 go to state 1, and oops, there's too many zeros there. And 0.05, sorry, too many decimal digits there. Too many decimal points. And 0.95, 90% remain in state 2, right? So now how are they distributed? So let's do a calculation, right? How many people are in state 1? Well, let's see. We had 70% back at the beginning. 90% of those remained. So 90% of the 70% remained in state 1. But we also gained some people, right? We gained 5% of those in state 2, which was 30%. Right, so just to clarify, these are the ones that went from state 1 to state 1. These are the ones that went from state 2 to state 1. So likewise, how many people, what proportion rather, is in state 2? Well, 0.1 of the ones that were in state 1, which is the 0.7, go to state 2. And 0.95 of the ones that were in state 2 remain there. So in other words, what we've got here we've got state 1 to state 2. Here we've got state 2 to state 2. So if we calculate these are easy calculations. So I did these ahead of time. This first one is 0.645. This is 0.3550. No, we don't need that last zero. So then let's look, what if this happens again? So now what? So we say, okay, well, state 1, right? So the same procedure. So 90% of the ones that were in state 1, which is now 0.645, remain. And we gain 5% of the other ones, 0.355. In state 2, we now have 0.1 of the ones that were in state 1, which is 0.355, plus the 0.95, the ones who remain in state 2. Sorry, this was I miswrote that. This was the 645, and the ones that remained, 355. So if we calculate these, this is 0.5983 and 0.4017. So if you notice, these can be represented by a matrix calculation. Like technically matrix multiplied by a vector. So let's see, right? The first one, right? Let's let me pick a different color. This one right here, we'll call that A, and B, I'll call this. So take a look at A and look at B. So in A, what we did is we did the matrix 0.9, 0.1, 0.05, 0.95. We multiplied that by 0.7, 0.3. And we got 0.645, 0.355. In the second matrix multiplication, it was the same matrix. Now we multiplied by the new figures. So you can see this is an iterative process, which we could repeat over and over again. That was sort of a redundant statement, there we go. So what I'll do is I'll clear the screen and I'll point out sort of the general rule for what's happening. But before I do, I just want to point some things out while we have all this data on the screen. If you look at this vector right here, this vector comes from this vector, or from this data, which we can think of as like what happens to people in S1. We'll say behavior of those in S1. And adjacent to it, of course, we have these right here. This is the behavior of those in S2. So you might see that this is like a nice matrix calculation. And so not only can this be represented as matrices, but we can also sort of scale this up. Like what if we had 3 states and people switching between them, or 4 states and people switching between them, and different initial states, right? Because if we look just for reference, let's pick a different color. So back at the beginning, this 0.7.3 was our initial state, and that is what we multiplied over here on the right to get the new state. And then we multiply by the new state to get the new state after 2 iterations, and so on. So we can start to see how this can be generalized. So let me pause here, clear the screen, and write down a general statement of how this calculation works. So 2, here's the general idea. So a population distribution can be represented by a vector. We'll say X. Right? So the entries in this vector add to 1 because that's the total population. We're going to formalize. All these have official mathematical names, and we'll get to that soon. But right now, I just want to see the pattern while it's all fresh in our heads. So the movement of these populations, or the movement of this population, this can be represented by a matrix. Actually, I'll do something first. Let me make this an x sub 0 at the beginning, because we can think of it as like a starting population. So the movement of this population can be represented by a matrix T. So this is called T. I'll sort of define this formally later. This is the T for a transition matrix. But basically what happens in this matrix, in which column J, this tells us what happens to the population in state J. So then the new population, or let's say the updated distribution, is then, we can think of it as an x1, like a new state, is you take that transition matrix and you multiply it. And then that is after one iteration. And then after two iterations, x2 will be t x1, which will be the same as t x0, which would be t squared x0. And then after 3, x3 will be t cubed x3, or x0. And of course, in general, after, we'll say, n iterations, x sub n will be tn times x sub 0. So this will work for any finite number of states. So here's an example. So I'm going to represent this by a picture. And so this picture also has a name. I'm going to call it a transition diagram. But the picture will make it clear what's going on. So I'll talk through it as I give it. So we're going to have three states. State 1. Let me actually number these. I'm copying this out of the text. So I want to number these accordingly so I'm not doing something that looks visually too different. So I've got three states right here. So what we'll say is, if you are in state 1, there is a 90% chance that you remain. So a little arrow going from 1 to 1, that's 90%. But if you're in state 1, you might also go to states 2 or 3. So suppose there is a 6% chance that you go to state 2, and therefore there must be a 0.4%, a 4% chance that you go to state 3. Notice these add up to 1 because everybody that is in state 1 does something. Right? So these have to add to 1. Right? Now if you're in state 2, let's suppose there's an 80% chance you remain. There's a 10% chance, let's say, you go to state 1, and therefore there has to be a 10% chance that you go to state 3. Now, suppose you're in state 3, we'll say there's a 10% chance you go back to state 1. There's a 70% chance. I'm just making these numbers up, by the way. Like, I'm copying this out of the book, but essentially this is just made up. And a 20% chance you go to state 1. So this matrix, or rather the matrix for this picture, is very simple. So what I do is I look at state 1 and I go, okay, if you're in state 1, there's a 0.9 probability that you stay in state 1. There's a 0.06 that you go to state 2. There's a 0.04 that you go to state 3. If you are in state 2, right, there's a 0.1 chance that you go to state 1. There's a 0.8 chance that you stay in state 2, and a 0.1 chance that you go to state 3. If you are in state 3, there's a 0.2 chance that you go to state 1, a 0.1 chance that you go to state 2, and a 0.7 chance that you stay in state 3. So if your initial population is, say, x0, so this distribution could be, for example, 0.1, 0.2, 0.7. So this is 10% in state 1, 20% in state 2, 70% in state 3. Then you could say, for example, let me do it over here so we can fit a bunch of things in. After one iteration, I would do t times x sub 0. And if you do this, you will get 0.25, goes up a bit. The next one goes up a little tiny bit. And the third one goes down. Again, they all add up to 1. Then after 2 iterations, I would do t squared x0. You get 0.3514, 0.2552, and 0.3934. So, etc. You can keep going forever and ever and ever and see how many happen. Like after 100 iterations, what happens. Right? So this is the general idea of what we're going to be looking at. So I'm going to stop here. In the next video, what we're going to do is we're going to do sort of a long-term behavior experiment. We're going to say, look, what happens after like 100 iterations or 1,000 iterations or 1,000,000 iterations? Like, what's it going to look like? And from that, we can start to figure out like some interesting things about these matrices, etc. So let me stop there.